Advanced nuclear propulsion for manned deep space missions. My interest in spaceflight dates to when I was about 10 years old and received as a birthday gift a popular book about the feasibility of spaceflight. From it I learned for the first time about Oberth and Goddard and of the possibility of reaching the moon with a multistage rocket. This occurred at the same time that Hahn and Strassmann announced the discovery of nuclear fission, with the possibility of an atomic bomb by a fission chain reaction. Having been born in Germany in 1929, I received my Ph.D. in physics under Heisenberg in 1955. Inspired by the 15-megaton hydrogen bomb test conducted by the United States in 1952, I have been deeply interested in the nonfission ignition of thermonuclear reactions by inertial confinement since 1954. At the time all fusion research in the United States was still classified, but I had quite independently discovered the basic principles of inertial confinement, the Gutterly convergent shock wave, and the Rayleigh imploding shell solutions. In 1956 I presented my findings at a meeting organized by von Weizsäcker at the Max Planck Institute in Göttingen. The abstracts of this meeting reside today in the University of Stuttgart Library. In 1958 I had delivered a paper at the Second United Nations Conference on the peaceful use of atomic energy on NERVA-type nuclear rocket reactors. The paper turned out to be of some importance as I was invited by the US government to come to the United States under Operation Paperclip. In San Diego I met Ted Taylor and Freeman Dyson, who were working on the famous Orion nuclear bomb propulsion concept. This concept is generally credited to Stanislaw Ulam, but I know from conversations I had with Heisenberg that a similar idea had been presented to Heisenberg by Werner von Braun in Berlin in or around 1942. Because of my idea to use the Gutterly convergent shock wave solution for thermonuclear ignition, Ted Taylor and Freeman Dyson were interested in my joining their group. But because at that time this work was classified and I was not yet a US citizen, this was not possible. In 1967 I saw a new possibility for the nonfission ignition of thermonuclear microexplosions by intense relativistic electron and ion beams, driven by a high-voltage Marx generator. This ignition concept could be used not only to control the release of energy by nuclear fusion, but also to propel a spacecraft, replacing the pusher plate of the Orion concept with a magnetic mirror, reflecting the plasma fireball of the thermonuclear microexplosion, reference 1, 2. This idea was adopted by the British Interplanetary Society in its 1978 Project Daedalus Starship study, replacing a neutron-rich deuterium-tritium, DT, thermonuclear explosive with a neutron-poor deuterium-helium-3, I3, explosive. Unlike the DT reaction, in which 80% of the released energy goes into neutrons, most of the energy in the DHE3 reaction goes into alpha particles, which can be deflected by a magnetic mirror. But because He3 is not abundantly available everywhere, it was proposed to mine it from Jupiter's atmosphere. Studies have been conducted on spacecraft propulsion with the matter-antimatter annihilation reaction, however, it is an enormous technical challenge to produce antimatter in appreciable quantities. The idea of using nanogram amounts of antimatter for the ignition of fission-fusion microexplosions appears to have credible potential, but even there the production and storage of nanogram quantities of antimatter pose serious technical problems. We have little reason to expect that new fundamental laws of physics that could lead to a breakthrough in propulsion still await discovery. Very much as America was discovered only once, it is quite possible that all the fundamental laws of physics relevant to propulsion have been discovered, challenging our imagination to find out if they are sufficient to invent propulsion systems that ultimately might bring us to Earth-like planets of nearby solar systems. I conclude this preface with an imaginary talk by Ted Taylor to Freeman Dyson as recorded by the latter's son, George Dyson, in his book Project Orion, The True Story of the Atomic Spaceship, followed by a dream of Ted Taylor's. Freeman's hope for the Orion had rested on the fact that there seems to be no law of nature forbidding the construction of fission-free bombs, and on the belief that improvements in the design of the nuclear devices, by reducing the fraction of total yield due to fission, might achieve reduction factors of 102 to 103. This belief in small, fission-free bombs has largely evaporated. One exception is Ted Taylor. He remains convinced that small, clean bombs could propel Orion, but he still fears more than ever that such devices would be irresistible as weapons, until we outgrow the habit of war. There are lots of different routes to that final result of a very clean bomb. Could you make a 1 kiloton explosion in which the fission yield was 0, which is bad news on the proliferation front, but could turn Orion into something quite clean? Freeman thinks Ted is wrong, and Ted hopes Freeman is right. I for my part think Freeman is wrong. Many years later, shortly before his death, Ted Taylor reported, "I had a dream last night, about a new form of nuclear weapon, and I am really scared of it." He reported that when he woke up, he wrote down his dream, and it appeared scientifically sound and feasible. What was it? We never will know with certainty, but I have a guess: it is the possibility of chemical superexplosives, explained in the appendix, powerful enough to ignite a thermonuclear bomb. Introduction. As Hermann Oberth proved for chemical rockets in his 1923 book The Rocket into Planetary Space, this paper will try to prove for thermonuclear rockets the following. At the present state of science and technology, one can build spaceships driven by deuterium thermonuclear reactions, able to reach the outer limits of the solar system. Such spaceships permit the manned exploration of the entire solar system and beyond, with the ultimate potential to reach nearby solar systems. The cost in research and development to build such spaceships will be high, but still well within what is economically feasible. Using the same physical principles as for deuterium fusion rockets will also lead to the realization of clean nuclear energy, justifying the expenditures for these large projects. Deuterium can be used as the rocket fuel of choice in addition to any inert material that is suitable as a propellant. This propellant material is available on most planetary bodies and particularly on the comets of the Oort cloud. The main idea is that by gradual radial expansion from the Sun, by building bridges over the Oort clouds, which presumably surround all suns, Earth-like planets in neighboring solar systems can eventually be reached. The first and most important step toward this goal is to reach the focus of the Einstein gravitational lens at 550 astronomical units. At this location, one can use the Sun as the lens of a super telescope, an idea first proposed by Claudio Maccone in 1993. Present knowledge is that there are planets in nearby solar systems that are likely Earth-like planets. It is only with this gigantic telescope that one can determine if life on these planets is possible. But because of the complexity of this task, a manned mission to the Einstein gravitational lens focus is likely to be needed, possible only with advanced nuclear rocket propulsion. Deuterium, argon ion lasers, and key superexplosives. The goal is a spacecraft that can be refueled while landing on a planetary body, which can be a planet, an asteroid, or a comet. With heavy water available on many planetary bodies but in particular on comets, this suggests the use of deuterium, D, as the thermonuclear rocket fuel. Ignition of deuterium, though, is more difficult than ignition of the deuterium-tritium, DT, reaction or of the deuterium-helium-3, Th3, reaction. The DT reaction is the easiest to ignite, but 80% of the energy goes into neutrons, which cannot be deflected by a magnetic mirror. In the Th3 reaction all the energy goes into charged fusion products, but in a mixture of D with He3 there are still some neutron-producing deuterium-deuterium, DD, reactions. More important is the fact that, unlike deuterium, He3 is largely unavailable. There is some indication of He3 on the surface of Moon. In the Daedalus Starship study by the British Interplanetary Society, it was proposed to mine He3 from the atmosphere of Jupiter. In either case, the cost to recover appreciable amounts of Na would be very high. For the DD reaction, the situation is quite different because there the instantaneous burn with deuterium of the T and He3 reaction products of deuterium makes possible a detonation wave in dense deuterium. In this detonation wave, only 38% of the energy released goes into neutrons, compared with 80% for the DT reaction. Deuterium can be extracted from water with relative ease in 3 steps. Water is electrolytically split into hydrogen and oxygen. The hydrogen gas, composed of H2 and Hd, is cooled down until it liquefies, whereby the heavier Hd is separated by the force of gravity from the lighter H2. The newly produced Hd is heated and passed through a catalyst, splitting Hd into H2 and Dz, according to the equation 2HdH2 plus D2. Since the gravitational field on the surface of a comet or small planet, from which the D2 shall be extracted, is small, the apparatus separating the liquid Hd from H2 must be set into rapid rotation. The comparatively small amount of energy needed for the separation can ideally be drawn from a ferroelectric capacitor, for example, a barium titanate capacitor with a dielectric constant E5000, to be charged up to many kilovolts by a small fraction of the electric energy drawn from the deuterium fusion explosions through a magneto-hydrodynamic loop. One can also draw this energy from a small onboard nuclear reactor requiring only a small radiator, slowly charging the capacitor. Alternatively, one may store the needed energy in the magnetic field of a superconductor. For the launching of the spacecraft into Earth orbit, a very different scheme is proposed. It requires special materials that are readily available on Earth but not on extraterrestrial bodies serving as landing points to refuel the spacecraft. There the primary resource is water from which deuterium is obtained. In the Orion bomb propulsion project, a large number of fission bombs, or fission-triggered fusion bombs, were proposed to lift the spacecraft into space. Since this would release a large amount of highly radioactive fission products into the atmosphere, it was one of the causes that killed Orion. Even though large payloads can be brought into Earth orbit by chemical rockets, this remains very expensive, and an acceptable less expensive nuclear alternative is highly desirable. There appear to be two possibilities. A laser driven by a high explosive, powerful enough to ignite a DT microexplosion, which in turn can initiate a thermonuclear detonation in deuterium. A second, more speculative possibility is the conjectured existence of chemical kiloelectron volts, Ki, superexplosives. These are chemical compounds formed under high pressure, resulting in Ki bridges between inner electron shells and able to release intense bursts of Ki X-rays capable of igniting a DT thermonuclear reaction, which in turn could ignite a larger deuterium detonation. To realize the first possibility, one might consider pumping a solid argon rod with a convergent cylindrical shock wave driven by a high explosive. If the argon rod is placed in the center of convergence and reaches a temperature of 90,000 degrees K, the upper ultraviolet laser level of the argon will be populated. Following this heating, the argon cylinder radially expands and cools, with the upper laser level frozen into the argon. The energy thus stored in the upper laser level can then be removed from the rod by a small Q-switched laser, the resulting powerful laser pulse optically focused onto a thermonuclear target. To realize the second possibility, one would have to subject suitable materials to very high pressure. These energetic states can be reached only if during their compression the materials are not appreciably heated, because such heating would prevent the electrons from forming the bridges between the inner electron shells. Magnetic insulation and inductive charging. Two concepts are of great importance for the envisioned realization of a deuterium fusion-driven starship. The concept of magnetic insulation, which permits the attainment of ultra-high voltages in high vacuum. The concept of inductive charging, by which a magnetically insulated conductor can be charged up to very high electric potentials.